Greetings all. This example is not going to be algebraically difficult, but it's a chance for me to test out some slightly different versions of the technology while showing you an example of converting a double integral in rectangular coordinates and writing them into a polar coordinate system. This particular double integral would not be challenging to integrate with our normal techniques and just power rules and substitutions. But I want to show you what happens when we look at the region of integration and try to write it in a polar form. So the region of integration has been one of my major themes as we've been going through this chapter on multiple integrals. And the concept is the dy dx boundaries, of which this would be what's going on with x, and this is what's going on with y. What does that look like in a two-dimensional region? And we've learned already that the integrand, the function within, it could represent the third dimension, which could be a volume, if this is all positive. Or it could represent a density function, and we could be finding the mass. And it has a number of other possibilities. We looked at surface area and different moments around axes. For this problem, though, we're just trying to write the problem as a polar integral and take away some of the physics concepts and the geometry concepts for just a bit. We've got boundaries. For x goes from 0 to x goes to 5. If I were to make a little homemade graph, you know, there's my x-axis and y-axis, so it's going to go from 0 to 5 on the axis. And the y boundaries go from y equals x, which is the lower boundary. Y equals x would be this line, y equals x, to y equals 5 is the upper boundary, which is a horizontal line. So what we'd be looking at is the region that's above the line y equals x and below the line y equals 5 in this first quadrant. It's pretty with all the colors, huh? So how do we write that into terms of polar? So let me slide things around here and add a little bit more detail. All right, so here is the graph that we just constructed in the first quadrant. You know, there is the x-axis. Let's change colors there. The x-axis is here, and the y-axis is here. And in a polar sense, we're not looking left and right and up and down. We're looking at what are the boundaries for theta, and what are the boundaries for the radius r. So theta begins its journey at whatever that angle is right there. Let's change colors to green here. There we go. So theta starts here, and then theta goes to this angle right here. With the line y equals x, it generates a slope of 1, which is an angle of 45 degrees, or in this case, pi over 4. So we're going to be looking at theta going from pi over 4 to a 90-degree angle, which would be pi over 2 radians. So those are going to become boundaries on our double integral for theta. The r boundaries are a little bit different. So let me come back here and do some work on the picture. The r boundaries go from the origin or the pole, and they extend out until we hit this horizontal line. Well, as I look at little, remember I called this my sprinkler system here. As we go from 45 to 90 degrees, the distance r actually gets shorter as we go from here to here along this pi over 4 to pi over 2 notation. So we actually have to look at this as the radius goes from the origin 0 to question mark, which appears to be whatever the line y equals 5 is. Well, that's not polar at all. So recall how we converted rectangular to polar equations. Y equals 5 is equivalent to stating that our sine theta is equal to 5. And if we solve for r equals 5 over sine theta, which is the same as 5 multiplied by cosecant theta. This becomes our upper R boundary. So we have theta going from pi over 4 to pi over 2, and r going from 0 to 5 cosecant theta. So we're now ready to go to our double integral and write this as a double integral. So let me slide a little bit further. So what happens to our double integral if we write it in polar coordinates? The function inside has values of x and y. X becomes r times cosine of theta, and y becomes r times sine of theta. And then the dy dx, we did this derivation in class, is r multiplied by dr d theta. And we just discovered that our theta boundaries go from pi over 4 to pi over 2. And our r boundaries go from 0 to 5 cosecant of theta. So there we have it, converted to polar. I'm not going to integrate this in this video, but this integral is something that we've done a similar problem to in class, so I encourage you and challenge you to make that happen yourself. Thanks a lot.